नमस्तुभ्यं वरदे कामरूपिणी विद्यारम्भं करिष्यामि सिद्धिर्भवतु मे सदा पद्मपत्रविशालाक्षी पद्मकेसरवर्णिनी नित्यं पद्मालयां देवी सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा।
Good evening, everyone. I'm Dr. Kothari, a radiologist from Narayana in Bangalore. Welcome to the first session of Pearls of Physics webinars from IACI. We'll directly begin the session, and these will be a long webinar series where we'll have one topic after the other. We'll be starting with the basics and gradually moving on to the cardiac CT and MRI bit of it. So today we have with us two, I can say, physics geeks who will be conducting the session. I would like to welcome Dr. Sanjaya Vishwamitra. He is our senior faculty today. He's the chairman of the Indian Association of Cardiac Imaging. He's the HOD at Satya Sai Hospital, Radiology HOD at Satya Sai in Bangalore. And he will be the mentor for the session today. Welcome, sir.
Thank you, Richa.
The speaker for today's session is Dr. Pudyavan. He is the consultant cardiothoracic radiologist at Kowai Medical Center in Coimbatore. And he will be talking today on MRI physics, basics of image formation. Welcome, Pudyavan.
Thank you.
Okay, over to you all for the session ahead.
Okay, is my screen visible? Yes, it is. Yeah. Okay. So thank you very much, teacher, for the kind introduction, and thank you, Sanjay sir. So I'm Dr. Pudyavan. I'm a consultant cardiothoracic radiologist from Kowai Medical Center and Hospital in Coimbatore. So I welcome all the delegates on behalf of IACA for this physics webinar series. This is going to be a very interesting series with a lot of interaction with the delegates. And we will try our best to make it as simple as possible. Physics is always considered a very daunting subject, especially MR physics. So we will not go too deep into it. We will just try to make it as simple as possible. And today will be the first session of this long webinar series. So the objectives of this series is to make an attempt at simplifying the basics of MR physics, and also to introduce the delegates to different hardwares that constitute an MR machine, what are the basic components of an MR machine, and introducing the listeners to the basic nomenclature related to MR, especially T1, T2, TR, flip angles, etc. and etc. We will also talk about the pulse sequences. We will start from the most basic spin echo pulse sequence, and we will move on to the advanced sequences also. What are these pulse sequences? Why are the pulse sequences actually needed? And if you're still with us after all this, then we'll also talk about various advanced sequences that are used, especially in cardiac MR. So this will be our first session. So In the first session, I'll be talking on the basics of image formation. So today what we will do is we will just get to know what is nuclear magnetic resonance and what is MRI or magnetic resonance imaging, a little bit of history, and what you need for an MR image formation, what are the basic components of the hardware of an MR machine, and what happens within the MR gantry, all the jargon of protons and vectors and lots of magnetic fields. So coming to a little bit of history. So the history of MRI started in 1946 with Felix Bloch from his Nobel Prize winning paper, which talked about magnetic moment, which is nothing but the spinning, his observation that the spinning nucleus acts like a small magnet. So any spinning nucleus acts like a small bar magnet is what his observation was, and that observation got him a Nobel Prize. And from this, we moved on with theoretical, then practical experiments on these concepts. And by the 1970s, Raymond Damadian and Paul Lauterbach, they used these nuclear magnetic resonance parameters, and they observed that these parameters can differentiate one tissue from the other. So the magnetic moment that is produced differs from one tissue to other depending on in which tissue that particular proton is present. So this brought about the generation of the first MRI images. The first MRI image took nearly 5 hours to obtain, and we got something of a blob kind of an image. And after this, everything is just, as we say, it's history. There was rapid advancement in understanding of the MR, and every manufacturer, every medical imaging equipment manufacturer started their research on MR, and there was exponential growth in all these pulse sequences and advanced MRI applications. So coming to hardware, so what do we need for an MR examination? The first and foremost, we need a magnet, because it is a magnetic resonance imaging. So the magnet can be either a permanent magnet, a resistive magnet, or a superconducting magnet. And the magnet configuration can be either an open magnet or a bore type magnet. Coming first to the permanent magnets. So as the name implies, this machine is made of magnets that are permanently magnetic. So we have, just like the small magnets that we used to play during our childhood, it's just a bigger and heavier magnet, which is permanently magnetized. And this is used for the magnetic field and image generation. So the problem with the permanent magnets is that usually the field strength is low, especially for clinical imaging. There are higher field strength permanent magnets that are available, but the area of imaging is so small that it cannot be used for humans. It is being used. There are 1.5 Tesla permanent magnet systems that are available for animal studies, but none for humans. And usually permanent magnets are in an open configuration. The advantages of a permanent magnet is that there is low power consumption and low operating cost. This is because the magnet is permanently magnetized, and we don't need electricity to produce magnetic field. And the permanent magnets also have a very small fringe field. And again, there is no need for any cryogen. So cryogen is a substance that is needed in superconducting magnets to keep the magnetic core cold. So since this is a permanent magnet, you don't need any cryogen. But the disadvantages of a permanent magnet is that the field strength is limited. Commercially available permanent magnets top off at 0.3 to 0.4 Tesla. And these are very, very heavy. Mind you, these are large blocks of ferrous or a ferrous-based alloy, which has been magnetized. So these will be extremely heavy. Installation will be very difficult. Installation in multiple story buildings will be nearly impossible, because the floor might not be able to carry the weight of the permanent magnets. And there is also no quench possibility. So what is quench? Quench is nothing but demagnetization of a magnet in an MRI machine. So in case of an accident or for routine maintenance, if you want to demagnetize an MRI machine, you do something called as quench. But this is not possible with a permanent magnet because they are permanently magnetized. So this is a disadvantage of a permanent magnet. Coming to the second type of magnets, that is the resistive magnets. So these are nothing but large electromagnets, and electromagnetism is nothing but when there is flow of electrons through a conducting material, a magnetic field is produced. So this is the basic of an electromagnet. So what we do here is we have a conducting material through which electricity is passed, and this produces a magnetic field. The problem with resistive magnets again is that they are available only with low field strengths. They can be either in bore type or it can be an open magnet, but usually it is an open configuration. The advantage of having a resistive magnet is that again, the low cost, because it just contains a conducting material and you just pass the electricity through them and magnetic field is produced, and lightweight. It doesn't heavy that much compared to permanent magnets. And another advantage is that it can be switched off. So suppose you want to switch off the MRI machine when it is not in use, you can just go ahead and switch it off and the magnetic field will be gone. And you can again switch it on and the electromagnet will start working and the magnetic field will be produced. So the disadvantage of having a resistive magnet is that it has a very high power consumption. So whenever you need a magnetic field, there have to be passage of current through the conducting material, and the field strength is also limited. There is one particular reason why there is high power consumption and limited field strength. This is because there is something called as resistance. So whenever there is flow of electrons in a conducting material, the material provides an inherent resistance to the flow of electrons. So this is called as a resistance, or resistance to the flow of current, or resistance of current, which is measured in ohms. So when there is resistance to passage of current, the energy that is lost during this passage is transferred as heat to the surrounding environment. So a resistive magnet will produce a lot of heat, and there is a lot of wastage of current because of the inherent resistance provided by the conducting material. And so these resistive magnets will require a good cooling mechanism. Usually it is water cooled. And also the other disadvantage of resistive magnets is that there is a very large fringe field, which can affect the surrounding environment. So ideally what we will have is that an electromagnet that doesn't have any resistance. So the main disadvantages of the resistive magnets is that we can't produce a high enough field strength, because a very high passage of current will produce a proportionately high amount of heat, and so the cooling mechanism will be overwhelmed. So ideally what we will need is an electromagnet that doesn't have resistance. So that's how superconducting magnets came to being. So what is a superconductor? A superconductor is any conductor that has zero resistance to passage of electrons through it. So it can be any conducting material, and if it offers zero resistance to passage of current, then it is called as a superconductor. But unluckily, humans don't know any known material that has superconducting capacity at room temperature. So there is no known material that can show superconducting principles at room temperature. So this will be a very good research field, and if any one of you can invent a conducting material that has superconducting properties at room temperature, then it will just solve all the energy problems of the whole world. So what we can do now is that this conducting material, if it is cooled to 4 Kelvin or almost minus 264 degrees centigrade, then that conducting material offers zero resistance to passage of current. So this is where the helium coolant comes into being. So what the helium does here in a MRI machine is that the helium cools the conducting surface of the magnet within to approximately around 20 Kelvin or minus 250 degrees centigrade, so that that conducting material becomes a superconductor. And once a material becomes a superconductor, it offers zero resistance to electron flow. So what happens is that you can pass a very little current into the magnet and produce very high magnetic fields, very high field strength magnetic fields with almost negligible amount of heat production. So this is how superconducting magnets came into being in MRI, because they are capable of producing very high field strength with a very high homogeneous magnetic field, and they produce hardly any heat. The second advantage is that they are also very low on power consumption compared to resistive magnets, because there is no resistance to electron flow. So you need not give a continuous potential difference to the magnet, and a small DC current will be sufficient to magnetize the magnet in a superconducting magnet. The disadvantage, it is a very complex construction, so the costs are high, and you need a cryogen, in this case helium, which can keep the conducting material at a very low temperature. Presence of acoustic noise from the magnets, mainly because of the gradient coils that are present. So these are the disadvantages of having a superconducting magnet. So this is how a superconducting magnet will look like. So there will be a bore, and it will have a conducting material in the center, which will be surrounded by a tank of helium, which will keep the conducting material to 20 Kelvin or minus 250 degrees centigrade, so that the conducting material remains a superconductor. And a high field strength magnet with a superconducting magnet and an open configuration is the ideal setup, but open configuration provides its own limitations in creating a homogeneous magnetic field. So we are somewhere in the middle. So we have a bore type magnets with high field strength, and we have open magnets where the field strength is not that high. Coming to the next hardware that is used in an MRI machine, it is radio frequency coil. So we spoke about the large magnet which produces the main magnetic field, and second is the RF coils. So these RF coils are used to transmit and receive the radio frequency signals. The RF coils can be majorly of two types: volume coils and surface coils. So volume coil is something where the examination area is at the center of the coil, and it produces an uniform field inside the coil. Whereas surface coil is a flat coil, but it has a very high signal to noise ratio. The downside is that the depth of penetration is very less. So if you're imaging a very superficial structure, then you can use a surface coil, whereas for deeper structures, you will need a volume coil. Quadrature coil is nothing but more than two volume coils which are combined together and placed at 90 degrees. And phased array coil are multiple surface coils which are connected in parallel, covering a large area. So the spine coil is an example of a phased array coil, whereas the body coil that we use is an example of a quadrature coil. And Faraday cage is nothing but a cage that is constructed around the MRI machine to insulate the MRI machine from the radio waves. So we have been talking about radio frequency waves which are emitted by the RF coils. So these radio frequency waves have the same frequency of any other radio waves that we encounter in the environment. So there will be a lot of interference if the MRI machine is not insulated from these radio waves. So we use a cage which is made of copper mostly, which insulates the MRI room from other environmental radio waves. And last but not the least are the gradient coils. So gradient coils are again electromagnets, but are of very small strength compared to the main magnetic field. And there are three gradients placed at orthogonal axes within the gantry. We name it as the X, Y, and Z gradient coils. So I will talk more about gradient coils later on. So now we have seen the most important hardware that are part of the MRI machine, which is the main magnet, which produces the B0 magnetic field, the RF coils, and the gradient coils. So coming to the physics per se. So what is nuclear magnetic resonance? So a charged particle, when it is spinning around its own axis, produces a magnetic field. This phenomenon is called as nuclear magnetic resonance. You can imagine this as the proton as an earth. So earth is a round proton which is rotating around its own axis, and it produces its own magnetic field with a north-south axis. So the magnetic field that is produced by the earth is approximately around 30 microtesla at the poles and around 70 microtesla at the equator. So 1 Tesla is equal to 10,000 Gauss. So the magnetic field produced by the earth is much smaller compared to the large magnetic fields that current generation clinical MRI machines produce, which is in the range of 1.5 to 3 Tesla. And one prerequisite for an element to demonstrate this nuclear magnetic resonance phenomenon is that the element should not have an equal number of protons and neutrons. So if there are equal number of protons and neutrons in the nuclei, their spins cancel out each other, and the magnetic field, because of their spinning, is not produced. So any element that has an unequal number of protons and neutrons will only be able to exhibit this nuclear magnetic resonance. And there are only a handful of elements and their isotopes that are capable of generating this magnetic resonance effect. So what we need for an MRI examination, so we need the MRI hardware. Again, then we need an element which has an unequal number of protons and neutrons in its nucleus, and which exhibits the nuclear magnetic resonance property. And hydrogen is the most abundant element that is present in nature, which exhibits the nuclear magnetic resonance property. So hydrogen consists of a single proton in its nucleus, no neutrons, and a single electron. So because its proton just contains one single proton and no neutron, so this produces the strongest magnetic resonance. And the nuclear magnetic resonance is measured by the gyromagnetic ratio of the particular element. And as you can see from this table, hydrogen has the largest of the gyromagnetic ratios of the all the elements that are MRI friendly. You can also, so here let me be clear that all these elements in this table are capable of being utilized in an MRI. But why do we use only hydrogen? This is because hydrogen is the most abundant element in organic matter. In our environment as well as in our body, hydrogen is the most abundant element, which is attached to water, attached to carbon in fat, and it is the most abundant element. Suppose, for example, we encounter an alien race suddenly, and if that alien race, so we humans and all organic matter in Earth are made up of carbon, hydrogen, and oxygen. Suppose an alien race is made up of, say, phosphorus and fluorine, then our MRI machine will not be able to image those aliens because they don't have an abundance of hydrogen in their body. So presence of hydrogen atoms is a prerequisite for our MRI examination for clinical purposes. So currently there are a lot of advancements in using these other elements for MR image generation. There are already various applications where phosphorus is being used, where phosphorus magnetic resonance is used to determine the presence of ATP in cells, and the energy metabolism of cells are imaged using MRI machines that is based on phosphorus elements. So for now, we will just consider about hydrogen protons. in our body. So as you can see here, in a resting state, when a patient or a person is in the general environment, all the hydrogen protons will be spinning randomly in different directions. So there will be no coherence or no between these hydrogen atoms in the body, and they all will be in different directions. So what happens when we place the patient within a MR gantry? So when the patient or any organic material is placed within the gantry of an MR machine, there is an alignment of hydrogen proton that takes place. This alignment can either be parallel, that is along the direction of the main magnetic field, or anti-parallel, which is against the direction of the main magnetic field. So when we say it is parallel or anti-parallel, the net magnetization is always in the direction of the main magnetic field. So this means that, for example, if there are 100 protons in our body and we are placed inside the MR gantry, what happens is that around 51 protons will be directed along the direction of the magnetic field, and 49 protons will be in the anti-parallel direction, and there are 2 extra protons which will be along the main magnetic field, and these 2 protons will provide the net magnetization and help in image formation. And apart from this parallel and anti-parallel orientation, there is something else that happens to the hydrogen protons, which is the precession. So precession is nothing but the angle at which the proton rotates to the central axis. This is similar again to the Earth, where the Earth rotates at a slightly tilted angle. So the precession frequency of the hydrogen proton is directly proportional to the gyromagnetic ratio and the magnetic field strength. Since gyromagnetic ratio is a constant for a given element, for hydrogen, the Larmor frequency will be directly proportional to the magnetic field strength. So at 1.5 Tesla, the Larmor frequency of hydrogen will be around 63.8 megahertz, whereas at 3 Tesla, the Larmor frequency will be absolutely doubled to that of the 1.5 Tesla. So when we place the patient in the magnetic field, what happens is that there is parallel and anti-parallel orientation of the protons, and the parallel orientation is slightly more than the anti-parallel direction, and that gives the net magnetization. And from now on, instead of talking about round nucleus, we will start talking about vectors. So vectors are nothing but a mathematical representation of the net magnetic field in the body. For example, in this case, when the patient is placed, there is a net magnetization that is in the direction of the B0 field. And we always denote the direction of the B0 field along the z-axis. So the vector will always be facing the z-axis where the net magnetization is. So this is how we denote the net magnetization. So instead of using this where there is a lot of nucleus which are in different directions, we use a simpler form of a vector in the form of a vector where we just denote the net magnetization, which is now along the direction of the main magnetic field. Coming to steps in image formation. So there are various steps in image formation. So we have got the hardware, we have placed the patient within the MR gantry. Now the protons are either in parallel or anti-parallel orientation, and we have found that the net magnetization is always along the main magnetic field. So the net magnetization, the patient is now lying in the MR gantry with the net magnetization along the external magnetic field. Now there are various steps in which we form the image from this patient. So the 5 main steps are excitation, relaxation, acquisition, computing, and display. So going to the first step. So excitation is a very, very, very simple process. So what happens is in excitation is that we give a radio frequency pulse into the body at Larmor frequency at a certain amplitude and for a certain duration. So what happens when an RF pulse is given at Larmor frequency is that the hydrogen protons which are precessing at the exact same frequency within the body will absorb the energy from this RF pulse and will be deflected from its resting state. So the resting state or the low energy state of the proton will be along the Z axis. And whenever it absorbs energy, it goes into the high energy state. And the high energy state will be in the XY plane. So I will introduce you to another term here, which is the flip angle. So flip angle is nothing but the angle at which the net magnetization is deflected into the XY axis. So the flip angle can be anywhere from 1 degree to 180 degrees. So, but for ease of understanding, I will just consider a flip angle of 90 degree for this explanation. So here, what we have done is we have given an RF radio frequency pulse at 63.8 megahertz, meaning that this is a 1.5 Tesla system. So the hydrogen protons were processing at 63.8 megahertz, and we have given an RF frequency pulse at 63.8. So the hydrogen proton absorbs this energy and is deflected by 90 degree into the XY plane. So that's about it, as simple as that. This is the first step in image formation, which is excitation. The second step. Now the second step is called as the relaxation. So as soon as the RF pulse is given and then stopped, as I told you, the hydrogen protons always would like to be in the low energy or the resting state. But once an RF pulse is given, it has absorbed this energy and it has gone into a high energy state. Now it will always try to go back to its low energy or resting state. So as soon as the first step of excitation is over, and as soon as you stop the RF pulse, the net magnetization will start again growing in the main magnetic field direction. And since this is a transfer from high energy state to a low energy state, the difference of energy is released into the environment as a RF pulse. So in this relaxation process, the RF energy that is absorbed from the RF pulse is again given back as a little bit of heat and a RF pulse into the environment or the surrounding tissues. So this process is called as a T1 relaxation or spin lattice relaxation. So why spin lattice relaxation? Because the proton, which is the spin, is giving off energy to its environment or the surrounding, which is the lattice. So T1 relaxation is also called as spin lattice relaxation, where the magnetic field, the magnetic moment that is along the XY axis is regrown along the Z axis with release of energy in the form of RF wave. So T1 relaxation is not the only process that takes place during relaxation. There are two processes that happen simultaneously. One is T1 relaxation and the other is T2 relaxation. So we have seen what T1 relaxation is. So what happens is that immediately after an RF pulse is given, that is at time 0, the net magnetization along the Z-axis is 0 because the magnetization is flipped into the XY plane. And as soon as the RF pulse is stopped, what happens is that the net magnetization starts to slowly grow along the Z magnetic field and it reaches the resting state or 100% with some time. So this particular curve is called as the T1 relaxation curve. So why is this T1 relaxation curve important? Because this T1 relaxation curve is different for different tissues. So for example, if the hydrogen proton is attached to water, the T1 relaxation will be a little bit different. Whereas if the hydrogen proton is attached to fat, then it will be different. If it is attached to liver parenchyma, then it will be different. So the rate at which the T1 relaxation happens differs from one tissue to other tissue. And this is the property that gives the excellent tissue contrast in MRI. And here we come across a term called T1 time, which is a time constant and is defined as the time it takes for the longitudinal magnetization to reach 63% of the original magnetization. So the time T1 is a time constant, and it is defined by the time taken for the net magnetization to reach 63% of its original value. Coming to T2 relaxation, which is again the another process which happens simultaneously. So for explaining T2 relaxation, you should know something called as phase or phase coherence. I will try to explain it with an example. So Republic Day is just a couple of weeks away, and everybody of you would have seen a Republic Day parade, and you will see the Jawans marching past in the during the Republic Day parade, and they'll be doing left, right, and everyone will be doing the same thing at the same time. So this means that they are all in phase. And if few of the soldiers are not doing it properly, then one's left leg will be in front, the other's right leg will be in front, one other's right arm may be in front. So when there is a discrepancy between them, then there is no phase coherence between the soldiers. So mind you, even though there is no phase coherence between the soldiers, they can still be moving forward. So presence or absence of phase coherence does not hinder their movement forward. So they can either move forward with phase coherence, or they can move forward without phase coherence. So similarly, T1 relaxation and T2 relaxation can happen simultaneously and are independent of each other. So moving forward is like T1 relaxation, where the net magnetization is gained along the Z magnetic field, whereas presence of phase coherence between the soldiers is like T2 relaxation. So what happens at resting state is that there is no phase coherence at all between the hydrogen protons. Each hydrogen proton will be directed at a different, the phase of each protons will be seeing a different direction at a resting state. But what happens is that immediately after radio frequency pulse is given, all the hydrogen protons will start becoming in phase to each other. That means that they point at the same direction. And as soon as the RF pulse is stopped, they will again start to dephase rapidly because their resting state has no phase coherence. So they will always be like to be in their resting state. So immediately after the RF pulse, they are in phase. And after that, with time, they will start to dephase. So this is what happens in T2 relaxation or spin-spin relaxation. It's called spin-spin relaxation because there is interaction between one proton and other proton, just like an interaction between one soldier and other soldier. So this is different to T1 relaxation, but happens at the same time. And as you can see here, immediately after the RF pulse, the magnetization is deflected 90 degrees into the XY plane. And after that, here all the protons are in phase or facing the same direction. But immediately they start to dephase, and after some time, they just become completely dephased and face all 360-degree directions. So here, immediately after the RF pulse, all the protons are in phase, that is 100%. And as soon as the RF pulse is stopped, they start to dephase rapidly. And after a particular time, there is absolutely no phase coherence between the protons. And this particular curve is called as a T2 relaxation curve. And just like T1 relaxation, the T2 relaxation is also different for different tissues based on to which element the hydrogen proton is attached. So T2 is again a time constant, which is defined as the time it takes for the spins to dephase to 37% of its original value. So the original value it will be 0%, and the time it takes for 100% of the protons to dephase to 37% is the T2 time of the tissue. So I'll just summarize T1 and T2. This might sound a little confusing. So T1 and T2 relaxation are two independent processes but happen simultaneously. The T1 is the regaining of net magnetization along the z-axis, whereas the T2 relaxation is the dephasing of protons in the xy plane. And as I told you in the example, they need not be interdependent on each other, and there can be in phase or out of phase movement of soldiers in spite of them moving in one direction. And these T1 and T2 relaxation are different for different tissues, which gives us the all important MRI contrast. And T2 relaxation is a much quicker process compared to T1 relaxation. So we have seen excitation, we have seen relaxation, and the third is acquisition. Acquisition is nothing but the RF pulse that is released by the proton during relaxation has to be acquired by us for image formation. So this is done by the receive coils. The receive coils can be standalone receive coils, which does the job of only receiving the RF pulse, or they can be a combination of transmit and receive coils, where a single coil both transmits the excitation pulse as well as receives the acquisition pulse. So the acquisition RF coils are always placed at right angles to the main magnetic field. This is because the RF pulse that is released by the proton when goes through the receive coils induces a current within the coil which is transmitted to the system. But if the RF coil is placed along this main magnetic field, what happens is that the magnetic field of the main magnet, which is much stronger in amplitude compared to the RF pulse that comes from the protons, will produce a much larger current in the receive coil, which will overwhelm the RF current produced by the RF pulse from the protons. So for this reason, the receive coils are always placed at 90 degrees to the main magnetic field. And the last step is computing and display. And so once the RF pulse is received by the receive coils, it is sent into a computer, and after maybe a second, you get the image. And it's as simple as that. No, actually, it is not that simple. Fortunately, I am the process by which the received electric current is transformed into images is not very much relevant to images like us. So fortunately for me, I need not go much deep into that, but we will talk about it at some other time. So these are the basic steps of image formation. So excitation, relaxation, which consists of T1 and T2 relaxation, then acquisition of the signal, and computing and viewing of the images. So now what we have reached to a point where we have got the hardware, we have placed the patient within the MR gantry, we gave an RF pulse, we excited the protons within the body of the patient, we got back a signal, and we are going to convert that signal into an image. But there are a lot of issues in this, because as I told you, the protons will precess at Larmor frequency when it is placed inside the magnetic field. So when a patient is placed inside the magnetic field, all the protons in his whole body will be precessing in the Larmor frequency. So if a RF pulse is given, we have no control over whether that RF pulse is exciting a proton in the head, in the chest, in the abdomen, or in the foot. So we absolutely have no control whatsoever till now. So to differentiate the RF pulse from different body parts or from different slices, we exploit some of the properties of the RF pulse, which is phase, frequency, and amplitude. And the solution for this issue, that to localize from where that particular RF signal is coming from, is the gradient coils. So as I told you before, gradient coils are nothing but electromagnets which are placed in the gantry in 3 different planes, and they provide additional magnetic fields in the X, Y, and Z plane. So there are 3 electromagnetic coils which produce an additional magnetic field in addition to the main magnetic field in 3 different planes. So the power of the gradient system is measured by something called as a slew rate. Slew rate is the ratio of maximum power of the gradient divided by its rise time. So ideally, when we work with the gradient, what theoretically we would like to have is that when we switch on the gradient immediately reaches its peak power. It stays in its peak power till the time it is switched on, and when it is switched off, it should immediately drop to 0. But this is only possible theoretically. Practically, what happens is that once you switch on a gradient, it has a slope where it gradually reaches its peak value, then stays at its peak value till it is on, and as soon as it is switched off, then it tails off and reaches 0. So the slew rate is nothing but the ratio between the maximum strength of the gradient divided by the time it takes for it to reach the maximum strength. So why is slew rate important? The higher the slew rate, the more steep is the curve, and more powerful is the gradient system. And a very powerful gradient system will give you scope for more advanced applications. So when you're buying an MRI machine, look for the slew rate of the gradient, and the higher the slew rate, the more powerful will be the gradient, and more advanced applications you will be able to run in that particular machine. So coming to our problem, so we had a problem that we were not able to localize from where a particular signal is coming from. So for that, we do something called as encoding. So there is slice selection, phase and frequency selection encoding from the 3 gradients. So in this example, if you see, this is the main magnetic field. The patient is lying within the gantry, and all the protons in the patient's body from head to foot are rotating at the same Larmor frequency. This is a 1.5 Tesla system, so it is rotating at around 63 megahertz. So now if you are going to give a radio frequency pulse, it will excite all the protons throughout the patient's body. But we don't want that. We want to image a particular part of the body. So for that, what we do is we use a slice selection gradient or a gradient along the z-axis for axial sections. So what we do here is we switch on the slice selective gradient so that it produces another additional magnetic field GZ in addition to the B0 magnetic field. So once an additional magnetic field is produced in this direction, the magnetic field at the isocenter remains unchanged, whereas on one side the magnetic field is more, and on the other side the magnetic field is less. And in the first slide itself, I told you that the Larmor frequency, or the frequency at which the hydrogen protons precess, is directly proportional to the magnetic field strength. So here we have a gradient of magnetic field where the magnetic field is greatest near the head and the magnetic field is least near the foot. So by default, the hydrogen protons will also start precessing at different frequencies based on their location. So the proton in head will precess at a slightly higher frequency, whereas the protons in the foot will precess at a lower frequency. Just make a note that these frequency numbers are just for illustration purposes. In reality, the differences in frequency will be very, very minute. So I'm just using these numbers for explaining the concept to you. So now, if you give an RF radio frequency pulse at a particular frequency like 63.7 megahertz, then that particular RF pulse will not excite the protons that are present in the foot or in the abdomen, but will excite the protons only in the head of the patient. So now we have solved one problem where we are able to selectively excite the protons at one particular slice of the body. So this is called as a slice selection. So now what we have got is an axial slice of protons. So we have excited an axial slice of protons using the slice selection gradient, but the signal that is coming from that slice, still we are not sure whether that signal is coming from the anterior part of that slice, posterior part of that slice, right or left. So for this purpose, what we do is something called as phase encoding. So phase encoding is done in a different direction, y-axis in this example. And again, this is another magnetic field which is applied from anterior to posterior. So when this phase encoding gradient is applied, what happens is that there is a mild difference in the phase of the protons at which these precesses. So this particular proton is phasing at a slightly different direction compared to this proton. So there will be a progressive change in phase of the protons from anterior to posterior. But each of these protons will still be rotating at the same frequency. So they will be still rotating at the same Larmor frequency, but the phase of these protons, the direction at which it phases, will be slightly different, starting from anterior to posterior. So now what we have done is we have selected a particular slice of tissue, and we have divided that particular slice of tissue into multiple rows based on the phases. And the third and the last encoding step is the frequency encoding step, which is applied along the x-axis. So again, this is another magnetic field that is applied along the x-axis, and it is applied during the acquisition part of the image generation. So what happens is here is that because of the slight change in the magnetic field in the x-axis, there is a again minor change in the frequency at which these protons are precessing, but the phase difference between the protons remains the same. So what we have done is that we have converted the human body into individual voxels, whereas the z-axis gradient is used to select an axial slice. The y-axis gradient is used to create rows in that axial slice, and the x-axis gradient is used to create columns in that particular slice. So what we have got is individual voxels of signal which has their own unique frequency and phase. And from this unique phase and frequency, we will know exactly from which voxel that particular signal is coming from. So the problem that we faced, that we didn't know from where that particular RF signal is coming from, is solved with the use of these gradients, because now we know from exactly which voxel that particular signal is coming from based on the frequency and the phase of that particular signal. So there is a complex mixture of frequency, phase, and amplitude that is received or acquired by the receive coils, which then, as I told you, goes through the Fourier transformation in the computers to give you a good quality image. So I'll just pause it here. So we will just go through what we have learned so far. Did we learn anything at all? I hope we did learn something at least. And so we learned that how each protons behaves as a small magnet. So each nucleus with an unequal number of electrons and protons will behave like a small magnet. And we use the hydrogen proton for image generation, mainly because it is the most abundant and it has the highest gyromagnetic ratio. And Larmor frequency is the frequency at which these protons precess, and this is directly proportional to the field strength. The higher the field strength, higher will be the Larmor frequency. And the hardware, so we have the main magnet that produces the main magnetic B0 magnetic field. We have RF coils for transmitting and receiving RF pulses. We have gradient coils for applying the slice, phase, and frequency selection gradients. we have the Faraday cage to isolate the MRI machine from environmental RF waves. And we also have very powerful computers that do the Fourier transformation for us. And the first two important steps in image formation is excitation and relaxation. And when we talk about relaxation, there are two things that are happening: T1 relaxation and T2 relaxation, which happens simultaneously but independent of each other. And gradients are the most important part of the MRI system, and these are used for encoding and localizing the particular signal. And now we have come to the most exciting slide of this talk, which is not about pulse sequences, but rather the penultimate slide of this talk. So I'm not going to talk about pulse sequences today. So till now we have learned how to generate an RF pulse from the body and how to localize it. But just getting a single RF pulse from a body is not sufficient for us. We need different types of applications. We need different types of contrast. We need T1 contrast. We need T2 contrast. We need susceptibility contrast. So to differentiate all these contrasts, we use something called as a pulse sequences. So I will talk about what is a pulse sequence and what are the various types of pulse sequences and how are they done in the next session. And thank you very much. I know that this is a very dry and boring topic. I've tried my best to make it as simple as possible. And I thank IACA for this opportunity, and happy Pongal to all of you. Thank you very much.
Thank you, Pudhiyavan. That was an excellent lecture. That was actually very, very simply put, and I think you did a fantastic job of talking about something which is relatively complex. We don't have any specific questions. I was trying to see if I could answer the questions as we move along. I think many of the questions are going to be discussed that are being asked are more to do with your subsequent talks. We have a lot of people who have basically said, thank you, sir, great presentation, well simplified, and so on and so forth. So I think you did a great job of taking a complex topic and making it relatively simple. So if I can ask you, you mentioned about, say, coils, and you mentioned about the different types of coils that are there very briefly. So is it important for the IACI delegates, for the IACI attendees, to know more about coils in detail, Pudhiyavan?
Yes. So coils are really important because there are a lot of factors that affect image quality, and one of the most important thing is placement of coils. Most of the times, a poor image quality can be attributed to improperly placed coils, or there are a lot of artifacts that are possible when the coils are not good or little damaged, which we just can't remove these things whatever way we try. So the first thing is that correct placement of coils, and making sure that we use the right coils is most important. The second is that there are different types of coils. There are coils for each and every part in the human anatomy. But it is not economically viable for a center to procure all these coils. But all these coils are basically can be divided into the 4 types that I talked about. They are either a volume coil or a surface coil, and either they are connected in series or they are connected in parallel. So most of these coils, for example, for cardiac evaluation, there are surface coils that are available exclusively for cardiac purposes, where the surface coil is placed over the precordium, which gives an excellent signal to noise ratio. But again, a body coil, which is a quadrature coil, can give almost 80 to 90% of what a surface cardiac coil can provide at a fraction of the cost, because body coil will be part of every other MR system. So yes, to answer your question, yes, it is important that we know about the coils and what are the different types of coils, and because it will be very much helpful for us to use specific coils for specific applications.
Also, what I found is that particularly when you're purchasing the magnet is the best time for you to discuss coils and basically negotiate a good quotation with the vendors. And that's when they actually tend to give you the best options for coils. And as you know, one of the exciting advantages we have with regard to coils is parallel imaging. And you need to have special type of coils for phased array coils for you to be able to do parallel imaging, and you want to basically understand coils better, as Pudhiyavan said. One other question is that, this concept of T1 relaxation and T2 star is going to be expanded more in subsequent lectures. But is it important to understand T1 from a cardiac perspective? Is there any particular reason why T1 and T2, just understanding individual properties of T1 and T2 is playing a more important role in cardiac imaging nowadays, Pudhiyavan?
Yeah, yes, sir. So one important thing based on T1 and T2 is the latest mapping techniques that have been come up. So T1 and T2 mapping is nothing but a T1 and T2 relaxation based technique. But what it does is that, as I told you, in the T1 relaxation curve, each tissue has its own T1 and T2 relaxation curves, and each tissue has its own T1 and T2 times at which the relaxation occurs. So these mapping techniques, what it does is that it gives you the exact T1 and T2 values of these tissues. So instead of an image-based analysis, which is basically a qualitative analysis where we just see the image and differentiate one part of the image from the other part by the difference in contrast, what this T1 and T2 mapping has done is that it gives you a quantitative data where it gives individual T1 and T2 values of each and every voxel. So when there is even a subtle change between adjacent tissues, which our human eye may not be able to perceive normally, will be easily picked up when we use these T1 and T2 mapping techniques, because this is a quantitative technique and it gives you the exact T1 and T2 value of individual tissues based on their relaxation curves.
Thank you again. And I think this is a very nice example, as Dr. Pudhiyavan said very clearly, as to why we need to understand MRI physics all the way from the very basics onwards, because everything that you learn is coming back in some way of shape or form as a practical tool for us to improve our imaging abilities in cardiac MR. And with that, I thank you all for your attention, and I hand it back to the organizers. Thank you again.
Thank you, sir, and thank you, Pudhiyavan, for the excellent presentation. It was not only simplistic, but extremely exhaustive and very well explained. A lot of questions, as sir mentioned, will be covered in the forthcoming series. So I just want to remind everyone, this is a series. We are going to conduct a number of webinars every month, and we will be covering all the entire MR and CT, especially the cardiac part in it. So you're welcome with all the questions. We hope to make it a very interactive session. The next one will be in February, and we will be sending across the invite to everyone. Like for this lecture, it will be free, but registration will be required. Hope to see you all next month. See you.
Richa, there was one question about whether these lectures will be available on the IACI website.
They will be, where we are recording them. They may not be free, and they might have a nominal amount. That will depend on the management, but they will be available later. Yes.
Thank you again.
Thank you, everyone. Hope to see you next month. Bye.